Yeah, so like I was saying, we're going to start today looking at the actual computational physics. And most of what I am going to teach, or nearly what I'm going to teach, is what I need you to know. I will not, we don't have the luxury of time. So we are just going to focus on what is needed. Are we clear?
Okay.
Yes, that's what we're going to focus on.
Yes.
Mostly, probably if you're going to look at examples on something, you're going to look at maximum of 2 examples to show how something is done, but you're not going to go beyond that. Then apart from that, you are also going to have tutorial questions. These tutorial questions are for you to practice with. Out of those tutorial questions, you will be getting an assignment to make sure that you are actually doing the things you're supposed to be doing. This assignment will have to be submitted. So let's most likely we can say after every topic, you will get an assignment. You get an assignment. Probably you get to work out 2 or 3 questions. Then after you work out these 2 or 3 questions, you have to submit them. Are we clear?
Very clear, sir.
Yes. So you have to write out whatever the answers are, work out the problem, then you submit them. Then I mark these things because you will need assignments. Then from these assignments, I'll be able to see if you are understanding what you're doing. If there's something which is wrong, which I will see from all your solutions, then we can rectify it. Then you have a test. We have to do 2 tests. So assignments, 2 tests. Then the labs. We can do the labs. We're almost done with the Python. So basically, probably one of our days, maybe the Saturday one, we can eventually, after we have done whatever it is we need to do for you to write the exam, there is also a component of the labs, so we can continue using that particular day for the labs. Either one of them, either Sunday or Saturday. Probably that's going to be after September, but I'll need labs from you. At maximum 5 labs or 6 labs. Okay. Yeah. So those labs. Why is there an echo? How many devices do you have on?
Just one.
Okay. Yeah. So assignments at the end of each topic, I'll give you questions, probably maybe 10 questions. Out of the 10 questions, you answer 2 or 3 questions for the assignments. So for each topic, these questions will become most likely also, the test questions will come from these tutorial questions, and most likely also your exam questions also come from these tutorial questions. So it benefits you when you actually work out these questions. Okay. So the first thing we want to look at is a topic on how to find solutions to what are referred to as nonlinear equations. These are equations which are not straight lines. For example, a quadratic equation, a cubic equation, or a bunch of other things which are not straight lines. Okay? So a nonlinear equation basically is an equation which is not related to a straight line. We know how straight lines are. Y is equals to ax plus bx, ax plus b, where your a is your slope, your x is your x coordinate, then b is your intercept, along those lines. But anything which is not a straight line is referred to as a nonlinear equation. Okay. Now, when you're trying to find solutions, that's what's referred to as root finding. So you're trying to find the roots. The roots, which are the solutions to an equation, are also referred to as zeros. The zeros of an equation, basically, this is the value of x where the function has got this form. F of x is equals to 0. So when basically you're looking for a value of x where the function has got a value equals to 0. Are we clear? So here, what you're looking for is what value of x, if you put it in this part, whatever function this is, it gives you a 0. That is what's referred to as a solution, as a root, or as a 0. So basically, there are different ways of working out some of these things. and we're going to look at three basic ones which we use when you're doing computational stuff or numerical methods. So, for example, there are other ways you can do this. For example, there are nonlinear equations like a quadratic equation. There are a number of ways you can solve a quadratic equation. You can solve a quadratic equation using factorization, using the sum of squares, using the quadratic formula. So that's factorization stuff, the squares, and also the quadratic formula. Those are ways of solving an equation which is not a straight line using pen and paper. And when you're solving an equation using pen and paper, basically that's what's referred to as working out a solution analytically. When you do something analytically, then you are basically working out on a paper. So you can find your whatever the answers are. Okay, so there are some equations, nonlinear equations, for example, the quadratic equation, which you can actually solve with a pen and paper, and you get your answers. The answers you get are your roots. Some quadratic equations, or sometimes you have one root, or you have two roots, or you have two real roots, or you have some roots which are complex and stuff like that. However, this family of nonlinear equations does not only refer to quadratic equations. There are also other equations which are nonlinear. I've mentioned cubic equations, then there are also a lot of other equations. Now, it so happens that some of these nonlinear equations, you can solve them using pen and paper, fine. But there are also others which you cannot solve using pen and paper. Are we clear? There are some equations you can work out with your pen and paper. That's fine. But there are also other equations, nonlinear equations, which you cannot work out using pen and paper. Of this form. You've got an equation which has got this form, but it's nonlinear. Some you can work out with the pen and paper, so you can solve this. We can find the solution analytically. There are others you cannot do that. It's just not possible. So you have to use other kind of methods, and those methods are what are referred to as numerical methods. And with these numerical methods, basically, we tend to, you can also do it with pen and paper, but we usually tend to use computers. We come up with some scheme of working out the problem, then you use a computer, then the computer does the problem for you much, much faster. We also use numerical methods. Sometimes even when we know that we can work out some solution with pen and paper, but sometimes maybe you've got these nonlinear equations and there are many. So if there are a lot, then you want to find the answer in the shortest possible time. And for you to do that, a computer could be a good thing to do. And we're going to do this also. Something similar to this. So there are times when you can actually work out something with pen and paper, but it might take you a lot of time. In such cases, you have to use a computer for you to find out what the answer is supposed to be, or what the roots are supposed to be. Okay, so basically, those are the two main cases where we use numerical solutions. The first one is where an equation you're trying to work out cannot be worked out using pen and paper. It does not have an analytic solution. If it doesn't have an analytic solution, then you have to use a computer, or you have to use a numerical method for that particular equation. The other case is where your equations are simple. You can work out an answer with an analytic with pen and paper, but the problem is there are many and you want a solution very fast. So in that case where you with so many equations which are simple but you want a solution fast, it's also a good idea to use a computer. So what we're going to, we'll make some assumptions about what kind of solutions we'll be looking for. So the first assumption we're going to make is that this particular function, f of x, whatever f of x we're going to be looking at, has got what is referred to as a single valued root. It only has got one answer. It can have some nonlinear solutions, sorry, nonlinear equations can have more than one answer, but in this case, we are assuming that there is only one answer in the area in which we are interested in. So that's the first thing we are assuming. Of course, that's not always the case. Sometimes there's more than one solution. So if there's more than one solution, we are just going to restrict ourselves to a particular range to ensure that we enforce this whole thing of only having a single valued root. The other assumption is that our solutions are actually real, they're not complex numbers. So with these two assumptions, one where we have got a single valued root, the other one where our solutions are going to be real valued solutions, there are two ways, there are basically two methods or two schemes you can divide how you're going to work out the solutions. And that's what one of them is referred to as bracketing methods, a bracket method. Another one is referred to as what is referred to as an open method. So we're going to start our discussion with a bracket method. So in a bracket method, basically you kind of make a plot. For example, there's an example somewhere here. For example, I've got this graph here. This is a graph of a function x to the power 5 minus 2 x to the power 3 2x to the power 2 minus 3. So this is the function we are interested in. Now, of course there is a lot of this function, but our interest is only in this region from 0 here up to 2 there, from 0 up to 2. Now, if you look at what this function is doing from 0 up to 2, you see right now at 0, the value of the function f of x is below this 0 here. So f of x is negative, and as f of x is negative, it comes there, it cuts the x-axis, then it goes all the way up like that, wherever it goes. So in our case, our interest is finding out what is the root, or what is the value of x, which gives this function, which makes f of x equals to 0. So basically we are looking for this here, where this function is cutting the x-axis. Is that clear?
It's clear.
Yeah. So with a bracketing method, okay. So with the bracketing method, what you do is you choose an interval. For example, I choose an interval, the interval between 0 and 2. From here, from this, then I'll keep on shrinking this interval. So using the values I've chosen here, 0 and 2, I'll come up with a new guess value. So I'll keep on shrinking this interval until it is very, very small enough that it's only enclosing this bit here. There. Until we have got a very, very small interval in which this function is going to pass. So using that interval, then we use that interval to guess what the value is supposed to be. So with a bracket method, with any bracketing method like the one you're going to look at, which is called bisection, you have to choose an interval. And once you choose this interval, you have to make sure that the answer or the root or the solution exists within this interval. Here, between 0 and 2, we can see that the answer actually exists somewhere close to 1.5 there. The reason why we can see that it exists is because you can see the line here, the curve, comes and cuts the x-axis. So you have to make sure that between the interval you've chosen, the function should be able to cut the x-axis in between this particular interval you've chosen. If you choose an interval of 0 and 1 here, if you look at 0 and 1, the function doesn't cut the x-axis in this particular interval. So if your interval is 0 and 1, this is a wrong interval because there is nowhere where as you can see from this graph, where the function cuts the x-axis. Are we clear?
Yes.
So you always have to choose an interval in such a way that as you choose this interval, you are sure this function is going to pass in between this interval. So the interval, basically this interval or this bracket you're choosing, you have to make sure that the function passes in between this bracket. If you choose a bracket or an interval in which the function does not pass, then even if you use that thing, you can't find an answer. Okay. So basically what we do with a bracketing method here, suppose that you have a function f of x which crosses the x-axis at some point. In any bracketing method, we start with some initial brackets, some two values between which we think the root or 0 is located. We denote the boundaries of the bracket as a for the lower boundary and b for the upper boundary, respectively as this. So this is how we write our bracket. The a is for the lower boundary, the one we are considering, so starting from this point up to a particular point, and we are sure that once we write something like this, then we know that we convince ourselves that in between a and b there is a root to this particular function. The function f of x cuts the y-axis, the x-axis in between a and b somewhere. If it doesn't cut the x-axis in between a and b, then it's not possible for you to find the answer. Are we clear? You always have to make sure that your function cuts the x-axis in between a and b. These bracketing methods are algorithms that allow us to successfully shrink this interval AB until we arrive at an interval that is close enough to the root, and then we stop. So after we choose this interval AB, what we are going to be doing next is we will be successively shrinking this interval. We don't increase it. Once you choose your interval, now the job is to make this interval smaller, or to make this bracket smaller, until we are sure this bracket is just hugs the curve wherever this function is passing. Okay, so we successfully shrink this interval until we arrive at an interval that is close enough to the root, then we stop. So in our case, we're only going to look at one method which does this, because this process is tedious. So we're going to look at a method called bisection. Okay, apart from bracketing methods, there are other methods which don't use brackets. These are called open methods. With these open methods, you just choose an initial value. Then once you choose this value, your initial guess value for what the root is supposed to be, then you put this value in what's known as an open formula or an open method. Then this formula you've come up with is going to give you a new value of the root. Now what you're hoping is that when you have a guess value, let's say we denote our guess value as x0, then we put this guess value into this open formula. Then we're going to get another guess value, x1. But what we are hoping is that x1 is going to be closer to the root of this function. So we keep on doing this. So we keep on getting, we have a guess value, we put it inside this formula. Then this formula, as we put this value in there, it's going to give us another value of x. Then we get that, look at that value of x, is it closer to the answer? Then we put it back in the formula, then it gives us another value of x, like that, until we are closer to what we think the answer is supposed to be. So next we put our x1 in our open method again, which is going to give us another guess value x2, which hopefully this is closer to whatever the answer is supposed to be. Then we keep on doing this until we are close enough to the solution. We can always see if we're close enough to what the answer is supposed to be by plotting a graph of these particular functions. We know how to plot graphs, so you can always have a good idea of what the answer is supposed to be. Okay? Yeah. So there are only two methods we're going to look at in this case. When it comes to open methods, there's something called a Newton-Raphson method, and there's something called a secant method. So we're going to look at two methods, two open methods, a Newton-Raphson method and something called a secant method. Okay? Now, these two ways of working out, finding solutions to nonlinear solutions, open methods where we're using bisection, bracketing methods where we're using bisection, and open methods where we're using Newton-Raphson method, they've got advantages and disadvantages. The advantage of the bracketing method is that if you have chosen your bracket correctly, you have chosen your bracket in such a way that you are sure that the function passes between your brackets, then you will always find the answer. Are we clear? If you have chosen the bracket properly, you will always find the answer. It's going to be slow, but it will always give you an answer. In the case of the open methods are faster, but sometimes you don't get the answer. Okay, so either sometimes whatever it is you have chosen takes you closer to the answer, or sometimes it doesn't take you closer to the answer. So you have to choose your things a bit more properly. So let's start with bisection. So here we have a nonlinear solution equation of the form. This f of x is equals to x to the power 5 minus 2x squared minus 3 is equals to 0. So this is the equation which we have. Then we want to use the bisection method, starting with the interval 0 and 2. So I have a plot, like I think I showed you here. We have a plot of this function in this particular interval 0 and 2. F of x, x to the power 5 minus 2x squared minus 3 equals to 0. In the interval 0 and 2, this is what we have. Starting from 0 here, so this is a lower bracket, the lower boundary, this side, and that is the upper boundary there. Now, as you can see from the graph, you can see that there is a solution in this interval because the function f of x actually cuts the x-axis here. Is that clear?
It's clear.
Yeah, so you can see from the graph that the function actually does this, cuts the x-axis from there. But if you do not have a graph, you can always find out if the function cuts the x-axis in this interval or not. How do you do that? Now, if you look from 0 here, or this side, this part here, you can see that the value of at any value of x, the value of f of x is negative because f of x is always below 0. Do you see that? Here.
Yes.
The value of f of x at any value of x before 1.5, f of x is negative. It has got a negative value. Then after 1.5, f of x starts having what? What kind of values?
They're above 0.
Yes, so which means they're positive. So f of x has got negative values, f of x has got positive values in this interval. So this is what you look for. You want to find out if the function at the lower boundary here, at the lower bracket, if the function, whatever the function is, you want to find out if the functions changes sign, if the value of the function becomes positive, then negative, or negative and positive, whether it changes from positive to negative. If the value of the function does not change, like in this case, it changes from negative to positive. If it changes from negative to positive, it means that it has cut the x-axis somewhere. Are we clear?
Yeah.
If the value of the
I just wanted to ask on how are we determining the interval?
we just choose it.
Oh, okay.
Yeah, that's what you have to choose an interval in which the function is going to cut the x-axis.
Mm-hmm.
As you can see, between 0 and 2, the function actually cuts the x-axis. Is that clear? Otherwise, if you choose something which is where the function doesn't cut the x-axis, you can't find the solution. So if the sign of the function f of x changes from negative to positive, then we know that the function cut the x-axis somewhere. If on the other hand, you work out the value of the function at a here at 0. In this case, it's negative. I work out the value of the function. At 2, it's positive. So here, at the f of x equals to 0, if the function is negative, f of x at 2, the function is positive. So I know that the function has moved from being a negative valued function to being a positive valued function. So it has changed sign from negative to positive. Are we clear?
It's clear.
So if the function has changed sign from negative to positive, it means that the function has cut the x-axis. That also means that there is a solution somewhere in this bracket or this interval you have chosen. Are we clear?
It's clear.
On the other hand, if the function at f of 0 is negative and at f of 2 is still negative, then it means that most likely the function has not cut the x-axis. It doesn't cut the x-axis. Because at both points, the function is still negative. And this is possible because we have made certain assumptions. We have made certain assumptions that the function is only going to have one value in this particular interval we have chosen. It's possible that, for example, this particular function, if you follow my mouse, it can go like this, then it goes up, it cuts, then it goes down, it cuts again, then it comes back here. It's negative. But if you do something like this, it means that the function is going to have two answers in this interval. Are we clear?
Yes.
We made the assumption that you can only have one answer in an interval. And the only way you're going to have one answer in an interval is if the function changes sign from negative to positive or positive to negative. So that's the first thing you're supposed to do. If you can't plot, you have a way of checking if a function is negative or positive at the lower boundary and the upper boundary, and see if this is going to do that. So basically, that's how we're going to do it. So we start with this. So we have an interval AB, which is equal to 0 and comma 2, like that. So in this case, AB 0, comma 2, A is 0 and B is 2. A is the lower boundary and B is the upper boundary, which is 2. Are we clear?
It's clear.
Next, we want to find, because we have to check if there's a solution in this interval. Before you do anything with bisection, you might end up doing something, then there is no answer. Before you do anything with bisection, you always have to check if there is a solution in this particular interval. So how do you do that? You find what the value of the function is at A, you find out the value of the function at B. So you find out f of A and you find out f of B. So in this case, f of A, our f is this one, f of x is equals to x to the power minus 5 minus 2 x squared minus 3. So f of A, which is equals to f of 0, because A is equals to 0 here. Are we clear? That's going to be equals to 0 to the power 5 minus 2, 0 to the power 2 minus 3, and this is going to give us minus 3. Because I've got 0 to the power 5, then 2 times whatever this raised to the 0 raised to the power, that's going to be 0. 0 times whatever it is going to be 0. So this is going to be 0 here. Here you're going to get a 0, then you're going to get a minus 3, so you end up with minus 3 here. So this is the value of the function at 0. It's minus 3. Are we clear? So f of A, which is equals to f of 0, is minus 3. Is that clear?
Yes.
So that bit has been done. Next, you work out f of B. B is 2, so you will find out f of B. F of B is equals to f of 2, which is going to be 2 to the power 5 minus 2 times 2 to the power 2 minus 3, and this gives you 21. This 21 is positive. Is that clear?
Yes.
Now, how do we use the value of f of a, which is equals to minus 3, and f of b, which is equals to minus which is equals to 21, to find out if there is a root? So the next thing we do is, next we check if a root exists in the interval 0, 2 by evaluating this product. So we multiply f of a times f of b. If the product f of a times f of b is greater than 0, meaning that if you multiply f of a times f of b, you get a positive number, then no root exists within the interval 0, 2. If the product f of a times f of b is less than 0, then a root exists within the interval 0, 2. Are we clear? So when you multiply f of a, which is in this case f of a is minus 3, multiplied by f of b, which is 21. So we've got minus 3 times 21. That's going to give us a negative number, right?
Yes.
Yeah.
It's a negative number.
It's going to be a negative number. That negative is showing you that there has been a change of sign from one part to the other part. So somehow the function changed from negative to positive or positive to negative. It doesn't really matter what happened. But if there is a negative sign, if you multiply f of a times f of b, then you get a negative, then it shows that the function crossed the x-axis in this particular interval. So here, f of a multiplied by f of b is going to be equals to minus 3 multiplied by 21, and this gives you minus 63. Minus 3 is less than 0. So this is negative. So the product is negative. So if the product is negative, then we know that a root exists. Okay.
It's clear.
If the product is positive, then a root does not exist within that particular interval. If you multiply f of a times f of b, then you get a number, a product which is greater than 0, then it's telling you that there is no root in that particular interval. Okay, so since the product f of a times f of b is negative, it shows that a root exists in the interval 0, 2. The change in sign of f of x from negative to positive shows that f of x cuts the x-axis within the interval 0, 2. That's what this thing shows. Are we clear?
Very clear.
Yeah, so you always have to check. You always need to carry out a check to show if there is a root, if there is a solution to whatever function equation you're trying to work in the interval you have been given, by carrying out this operation, by multiplying f of a times f of b. Then after you do the multiplication of f of a times f of b, then you check if f of a is greater than 0, it means that there is no root in the interval you've been given. If f of a times f of b is less than 0, then it means that a root exists. So now that you have confirmed that a root exists, the next thing we're going to do is we're going to work out a new root. We're going to guess what the root is supposed to be. We are going to guess the root, what it's supposed to be. And the way you guess the root is simply by adding the lower interval and you add the upper interval, a plus b, then you divide them by half. So you add a plus b, then you divide by half, then you get what's called c, which is the midpoint. So always, with bisection, you always guess the root to be the midpoint of your interval. Are we clear?
Yes.
So in this case, our a is 0, our b is 2, a is 0, our b is 2, so we're going to say c is equal to half 0 plus 2, which is going to 2. 2 divided by half, that's going to give you 1. So this C is equals to 1 becomes your guess root. Your first guess. You're guessing what the answer is supposed to be. So here you are, 1. You've seen where 1 is? Here. It's clearly not the answer, as you can see, because at 1, our function f of x has got a negative value, right? The answer itself is much, much closer to 1.5 than it is to 1. Is that clear?
It's clear.
But the reason why we are doing this, why we are guessing, say, we add the lower boundary A plus the upper boundary B, then we divide by half, is because we want to come up with a way of making this bracket smaller. Are we clear? So the point here is we want to move this 0, this lower boundary here, which is at 0, we want to move it at 1 so that it becomes 1. When we do that, we will shrink our boundary from 0 to 2. It will become 1 to 2. So now our boundary will be much smaller. Are we clear?
I'm not clear there, just go through again.
We are saying that the reason why we are looking for a guess value is because we want to find a way of shrinking the boundary. We want to make our interval smaller. Right now the interval is 0 to 2. Right? But we want to find a way of making this interval smaller. And that's where the C comes in. That's where the value of C comes in. Now, if you look at what you've worked out, we have worked out that C is equals to 1, right? Hello? We have found out that C is equals to 1 here. Is that clear? Hello?
Yes.
Okay, now if you look at C is equals to 1, from this graph, in which boundary is the answer? Is it between 0 and 1 or 1 and 2? In which bracket is the answer? The root. Is it between 0 and 1 or between 1 and 2? Which bracket has got the answer?
Pardon?
Which bracket has got the answer we're looking for? Is it the one from 0 to 1 or from 1 to 2?
I think it's from 1 to 2.
You don't even have to think, you just look. You just have to look, because between 0 and 1, the function doesn't cut the x-axis. Does it cut the x-axis between 0 and 1?
No.
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 So if we are sure with this guess value, say the guess value is 1, then we look at 1 and 0. Between 0 and 1, the function does not cut the x-axis. Then we can move our lower boundary from 0 so that it becomes 1. Are we clear? Is that clear?
Yes, it is.
So once our lower boundary now becomes 1 here, we are going to have a new bracket 1 and 2. Okay? We're going to have a new bracket 1 and 2. And then we'll repeat the process again. So let's see how we do the process. So, after we work out our midpoint, C is equals to 1, the next thing we're going to do is we're going to work out this bit. We're going to work out what is the value of the function at C. Are we clear?
Yes.
So basically we are asking what is the value of the function at 1. From the graph you can see the value of the function at 1 is negative. Here you can see from the graph that the value of the function at 1 is negative. So, and this is what we have here. So f of c is equals to f of 1, which is equals to 1 to the power 5 minus 2 times 1 to the power 2 minus 3, which is equals to minus 4. So f of c is a negative. After you find f of c, you check if between a, which is a lower boundary, and c, which is a midpoint, if there is a solution between a and c. Here, you check if the function between a, which is here, a is equals to 0 and c is equals to 1, if there is a solution here. How do you check if there's a solution? You check if there's a solution by multiplying the value of the function at a and the value of the function at c. If you multiply f of a multiplied by f of c, if the product of f of a times f of c is positive, then it means that there is no solution. If the product of f of a times f of c is negative, then it means that the function cuts in this particular interval. The same thing we did at the beginning. How do we find out that there is a solution in an interval? We work out the value of the function at those particular intervals, then we multiply the value of the functions at those particular things. Then if the product is positive, then we know there's no solution. If the product is negative, then we know there's a solution. Are we clear? We do the same thing we did earlier. This time we multiply f of a times f of c. We want to find out if there is a solution between a and c. C is our guess value. We want to find out if there is a solution between a and c. Is that clear? What we are trying to do?
Yes, it is.
So f of a, we know f of a is minus 3. Then f of c is what you have found here, it's minus 4. So minus 3 times minus 4, this is going to give you 12. 12 is greater than 0, so this is positive. Since the product is positive, f of a times f of c is positive, this means that there is no answer between a and c. Are we clear?
Yes.
Between a and c, a is 0 here, c is 1. So between a and c, there is no answer. If there is no answer between a and c, then we can make a become equal to c. Because a is the lower boundary of the bracket and b is the upper boundary. So if between a and c there is no answer, then we make a become equal to c. Or we make c become a. So that we have a new lower boundary. So here our lower boundary was 0. Now when we make c become equals to a, then we're going to have a new lower boundary a here, where there is c here. Here. So we're going to do this. So c is going to become a, and when c becomes a, then a is going to become 1. Then the same way, this bit here, I think not the product here, f of a is going to become equals to f of c, which is equals to minus 4. So our new interval or a new bracket is going to now become ab equals to this one is supposed to be equals to here. The dot here is supposed to be equal. So our new bracket AB is going to be equals to 1, 2. So this will be our new bracket 1, 2. Are we clear?
It's clear, sir.
Yeah, the odd one was 0, 2. Now, after we have found the midpoint, which was 1, then we check if there is a solution between A and C, which you have seen there is no solution. Then we make C become A, which is equal to 1. Then the value of the function f of C becomes f of A, which becomes minus 4. So now that we have got a new bracket, A equals to 1 and B equals to 2, we work out a new guess value. We work out a new midpoint. So our new midpoint, now that we have got a new A, our A is 1, then our B is still the same, 2, then we can work out a new midpoint C. So C is going to be equals to half A plus B. Always, when you work out the midpoint, you add, then you divide. So A plus B divided by half. So in our case, our A is 1, our B is 2. So 1 plus 2 is going to be 3. Then 3 divided by half, that's going to give us 1.5. So our C, our new guess value, is now here at 1.5. Very close to the answer. Okay? So that's our new guess value, 1.5. Very, very close to the answer. So what do we do with our C? Now, with our C at 1.5, we check if the answer, the root is between 1 and 1.5. We check if the answer or the root to this equation is between 1, which is A, which is equals to 1, and C, which is equals to 1.5. So for us to do that check, we need to find out what the value of C is at 1.5. So f of C is equals to f of 1.5. So that's going to be f of C is equals to f of 1.5 to the power 5 minus 2 times 1.5 to the power 2 minus 3, which gives us this value here, 0.09397. This is a positive value. F of A, from what we have here, remember this bit here, the dot, is not the dot, is supposed to be an equal sign. So F of A is equals to F of C previously, which is equals to minus 4. So our F of A and our F of A is now 4. So here if we multiply, after we find our F of C, we multiply F of A, which is minus 4, and F of C, which is what you have here. So you're going to end up with F of A multiplied by F of C. Basically what you're trying to do here, we're trying to find out if the answer to this equation lies between A and C. So when you multiply F of A times F of C, so F of A is minus 4 multiplied by F of C, which is what you have here, and this gives us minus 0.375, which is a negative value, which is less than 0. Because this product F of A multiplied by F of C is less than 0, it means that the answer lies between A equals to 1.5 and C equals to, A equals to 1 and C equals to 1.5. That's where the answer is. Because when you multiply F of A times F of C, F of A is here, this is negative, and F of C is there at 1.5, it's just slightly positive. So you can see that this equation cuts the x-axis just before 1.5.
It's
Is that clear?
It is clear.
If the equation, if the curve cuts the x-axis just before 1.5, it means that there is an answer between 1 and 1.5. But between 1.5 and 2, there is no answer. Are we clear? The solution is between 1 and 1.5. It's not between 1 and 2. Is that clear?
It's clear.
So, if there is no solution this side, then we can shrink. We can make our C become B. So we shrink, we move this thing this side. We make the upper bracket become 1.5. So that our new interval is going to be between 1 and 1.5. Is that clear?
Yes.
So after we do that, so this is what we end up with. So we end up with, now we say, okay, fine, since the product f of A times f of C is negative, the negative sign shows that between A and C there is an answer, right? Therefore, we make C become equals to B, and B is going to become 1.5, and also f of C is going to become f of B, which is going to be equals to this 0.09375. So our new bracket is now going to become, AB is now going to become 1 and 1.5. So the lower part is going to be 1 and the upper part is going to be 1.5. Are we clear?
Yes.
Okay, so basically this is how this process works. So right now, what we started with a bracket which was equals to 0, 0,2. Then we shrunk it to 1,2. Now we are to 1,5, 1,1.5. So what we are saying now is that we think the solution is between 1 and 1.5. So now that we have got a new bracket between 1 and 1.5, the next thing is we are going to work out a new guess value, a midpoint. Always, our guess values are midpoints. Now that we have got an odd 1 and a new 1.5, we're going to use this A and B to work out a new midpoint. C is going to be equal to half A plus B. So in this case, our A is 1 and our B is 1.5. So that's going to be 1 plus 1.5, which is going to be 2.5. Then 2.5 divided by half, then you end up with 1.25. So this is now our C, our guess value C. So C is 1.25. After we find a C, which is 1.25, 1.25 is supposed to be somewhere in the middle here. Somewhere in the middle here. 1.25, somewhere in the middle here. Between 1 and 1.5, somewhere in the middle here. So this is where our new C is. Then we find out if there is a solution between A, which is 1, and C, which is 1.25, which is there. As you can see from the graph, there is no solution because the graph is still below the x-axis between 1 and 1.25. 1 is here, the function is negative. 1.25 is supposed to be here, the function is still negative. So there won't be any solution. Are we clear?
Yes.
If there will not be any solution, then we'll shrink. We'll make our C become A so that our boundary now comes here. It becomes 1.25 and 1. So we keep on doing that until we make our boundary as small as possible, until we are happy with what we have. Then finally we can work out our final guess value. So in this case, now that we have got a C which is equals to 1.25, then we work out what is the value of the function at C. F of C is equals to f of 1.25, and this is going to be equals to what we have here. So f of C equals to 1.25 is equals to 1.25 to the power 5 minus 2, 1.25 to the power 2 minus 3, and this is going to give us this, minus 0.073424186. What's important here is that this number is negative. Are we clear? This number is negative. Then we want to see if there's a solution between A and C. So how do we find out if the solution between A and C? We multiply f of A times f of C. If f of A times f of C comes out positive, then we know there's no solution. If f of A times f of C comes out negative, then we know there's a solution. So in this case, f of A is at 1. f A is 1. So that's minus 4. Then f of C is f of A is 1. So f of A is minus 4. Then C is 1.25, and f of C is what we have found here. So that's going to be minus 4 times what we have there, and this whole thing comes out to be 12 point something something something, which is greater than 0. So when you multiply f of A times f of C, what you get is a positive number. Are we clear?
Yes.
This positive number means that there is no solution between A and C. Is that clear?
It's clear.
If there is no solution between A and C, therefore we make C become equals to A. We make C become equals to A. So C, which is equals to 1.25, now our A becomes 1.25, and f of C, which is equals to this, that becomes our f of A. So like this. So we make this adjustment. So C becomes A, which would be 1.25, and f of C, which is this bit here, becomes this guy here. So we end up having a new interval which has been shrunk. So our A is now going to be 1.25. Our B remains what it is. So we end up having 1.25, then comma 1.5. So our interval has now shrunk further to this. So it's much smaller than what we had before. So with this new interval of what A equals 1.25 and B equals 1.5, again we work out a new midpoint, C, using these updated values, 1.25 and 1.5. So in this case, our A is 1.25, our B is 1.5. So in this case, C is going to be half A plus B, so that's going to be C equals to half 1.25 plus 1.5, and this is going to be equals to 1.375. So this becomes our new C. C becomes 1.375. Now, when you have got a C, a new value of C, the whole game is you want to find out if between A and C there's a root. If the answer is there, fine. If it's not there, then you switch. So after you find C, you have to evaluate f of C, which is equal to f of what? This whole thing here. And if you work out here, f of C is equal to f of 1.375. You get your what you have here, minus 1.866, this thing here. This thing which you have here is a negative value. Then you work out f of A times f of C. Why are you doing this? Because you want to find out if there is an answer between f of A and f of C. So f of A, our f of A is now this, up here. This is our f of A. It's negative. And our f of C is what you have here. It's negative. So now when you multiply negative times a negative number, you get a negative number. You get a positive number here, 5.735 something something greater than 0. So that's positive. Since this product is positive, it means that between A and C, there is no answer there. Are we clear?
Yes.
So we make C, which is 1.375, become A. And A's value, the value for A changes to, it becomes 1.375. Also, similarly, we make f of C become f of A, and we end up having this. So now we're just changing the A changes. So now with that, you end up having an f of A and B. So your A is going to be 1.375 and your B is going to be 1.5. So now we have an interval which is much smaller than what we started with. There's still some space there, but it is much smaller. Then you work out a new value of C. So now our A is 1.375, our B is 1.5. So in this case, we work out a C. New C is going to be equal to half A plus B. So our A is going to be 1.375 plus 1.5. So this is going to be, whatever it is divided by half, is going to give you 1.4376. So this is going to be a new C. Now, if you've got a new value of C, you want to find the value of the function at C. The reason why you're trying to do this is because you want to check if there is a solution between A and C, C being your midpoint. So work out the value of the function at C, like that, f of C. So you do that. So when you do that, this is what you get. F of C is equals to f of 1.375. This whole thing, this gives you a negative minus 0.994637489. Okay, so you work out this, the product of f of A times f of C. So f of A is what we have here. F of A is this one. That's a negative. Then our f of C is what you have here. So a negative, so you end up having f of A times f of C, which is a negative multiplied by a negative, then you get a positive. That positive is greater than 0. So basically what that means is that between A and C, there is no answer. Are we clear?
Yes, it is.
Yeah. So if between A and C there is no answer, then you make C become equals to A. So now A is going to become 1.4376, and f of C is going to become f of A, and the value of f of C is going to be this. F of A is going to be that. So now your new bracket is between AB. Now it shrinks further. Now it's between AB is 1.4376, 1.5. So you can see now the spacing between these brackets is somewhere 0.5. It's become smaller, 0.5. Close to 0.5, yes. Actually, not 0.5, 0.1. Less than 0.1. Okay. Next, you work out a new value of C. So using this A 1.4376 and B 1.5. So C is going to be equal to half A plus B. So that's going to end up C is equal to half 1.4376 plus 1.5. Then you end up with this as your value of C. Then you work out what this value of how much is this? What is f of x at C? And f of x at C is this. It's negative minus 0.47856569,557. Okay. Then you want to find out if between A and C, your new C, there's a solution by multiplying f of A times f of C. Now, f of A is this one, it's negative. F of C is this one, it's negative. So when you multiply f of A times f of C, so you end up with a negative number multiplied by a negative number, you end up with something which is positive, which is greater than 0. So basically that shows you that there is no solution between A and C. So if there's no solution between A and C, then you make your C become A and your f of C become f of A. So your C now your A now becomes 1.4688. Are we clear?
Yes.
Yeah. So your new interval now, which has shrunk, now becomes AB is equals to open bracket 1.4688, 1.5. Like that. I think we can do one more. you can work out a new guess value for C using this and that. So that's going to be A is equals to 1.4688, and then a B 1.5. So your C is going to be equals to half A plus B. So when you do that, you end up having this half 1.4688 plus 1.5. You end up with this 1.48844 as your guess value. Next, after you find your guess value, you work out what the value of the function is at the midpoint, which is this, and the function at the midpoint is what you have here. The value of the function midpoint is what you have here, minus 0.19883.296. This is negative. So why are you trying to find out the value of the function at the midpoint? The reason again is because you want to find out if between A and C there's a solution there. If between A and C there's a solution, fine, you change the boundary accordingly. But if there's no solution, then you can make C become A. So in this case, f of A and f of B. So f of A is what you have up here. F of A is this. That's our f of A. Then f of C is what we've just found here. This is our f of C. So you multiply f of A times f of C, so which is this negative number times this negative value. Then you multiply them, you get a positive value. So again, it's telling you that there's no solution between A and C. So if there's no solution between A and C, then you make C become equals to A. So now your A becomes 1.4844, and your f of C becomes f of A, which is going to be equals to this. You can continue to do this, I think. Yeah, you can continue to do this. If you do that, you work out your new C is equals to be half A plus B. So your A is this here. This is your A. Then your B is this bit here. So you work out a new C. So it's going to be half 1.4844 plus that bit. You end up with this. Then you work out, after you find your midpoint, your new midpoint C, then you want to work out what is the value of the function at the midpoint, f of C. And the value of the function at the midpoint f of C is this. With this new midpoint you have found, you want to find out if there is an answer or if there is a root between A and C by working out this product, f of A times f of C. F of A times f of C, this is going to be the value for f of A is that negative. The value f of A, or f of A is what you have here. This is our new f of A. So that new f of A times our new f of C, which is this here. So you've got negative times negative, you get your positive greater than 0. So that shows you that there is no answer between f of A and f of C. If there's no answer between f of A and f of C, then C becomes A. So you end up having C equals to 1.4922. This is your C, and your f of C becomes minus 0.045, this whole number this side. So as you can see, and our interval is this now. AB is now 1.4922, 4922, and the other one, our B is 1.5. So these are very, very close. Now our interval has become very, very small. Are we clear?
It's clear.
Yeah, our interval has become very, very small. So now, when the interval becomes small, you work out a final C, a final guess value. Okay? So work out a final guess value. When you do a final guess value, so that's going to be C is equals to this. So your C is going to be equals to half A plus B, and that's going to be equals to C is equals to half 1.4922 plus 1.5, and this is going to give you 1.4961. So this is going to become your value of C. With this value of C, then you can find out what value the function has. The function at this particular point at C equals to 1.4961 1.4961. Work out the value of the function here, f of c, which is equal to 1.4961. When you work out this whole thing, it gives you this much, 0.18912,834. So that's what you get. So we stop here. It's not exactly f of x equals to 0, but it's very, very close to 0. So basically, when you're doing these methods like bracketing, you don't actually come up with your answer. The answer you're going to find will not give you exactly f of x equals to 0. Are we clear?
Yes.
These solutions will not give you f of x exactly equals to 0. They will give you something which is very, very close, which you can live with. So in this case, the answer to our equation, the root to our equation is x is equal to 1.4961. So basically, this is the whole idea behind the bisection method. You start with a bracket, then you make sure in this bracket that there is a solution. Okay? Then from that solution, if the function or the equation cuts somewhere in the middle of this bracket, then after that, you start shrinking the bracket. Are we clear? There is an example number 2. This example number 2 is what you're going to look at tomorrow. So here, example number 2, find the root to the equation f of x is equal to cos x minus x plus 1 equals to 0, with the bisection method starting with the interval 1 and 3. So basically the interval I'm looking at here, I've shown more than this is a function. You see here, that's a function. There's a mistake. So here, so I'm supposed to probably start with 0 and 3. Yeah. So I need to update this for tomorrow so that we can, yeah. So we'll start from 0 here and 3. Yeah. 0 and 3. Somewhere there. Okay. So this is, again, we're going to look at another example for bisection, because bisection, we want to look at 2 examples because there's going to be a problem for bisection. You're going to have an assignment problem for bisection. You're going to have a test question for bisection. You're going to have an exam question for bisection. So this has to be understood, because after this, we're done with this second example here. You will get, when you're done with this topic, you will get assignments. There's going to be a problem in bisection in the other methods. So basically, the first assignment you're going to have is going to have 3 questions. One on bisection, the other one on Newton-Raphson method, the other one on the second method. Are we clear?
Yes.
Okay, so see you tomorrow. 15 hours?
Okay. No problem.
Yeah. Watch us.
I'm asking if you could upload it also on YouTube.
Yeah, I'll upload the video, but I also send you the notes on WhatsApp. This note on WhatsApp.
All right.
Yeah.
Okay, thank you.
All right.